All right, section 1.5 is titled Limits Involving Infinity. And part of what we're going to do, in fact, the whole first page of your notes is algebra. So depending on how recently you've done a college algebra, an algebra 3, algebra 2, pre-calculus kind of course will depend on how recent this is and how sort of fresh on your mind it is. So to start with, we're going to talk about the basic rational equation 1 over x. And go ahead and sketch that graph on your screen, or on your paper. I'll graph it on the screen. So the graph of 1 over x looks something like this. And we can talk about this graph having two asymptotes. So asymptotes are sort of loosely defined as lines that we can get very, very close to, and at least on the ends of those graphs we don't touch them. We would say this one has a vertical asymptote, it's the y-axis, and it has a horizontal asymptote, which would be the x-axis. Okay? And the reason is because we can't plug in 0 for x, obviously, right? And likewise, we can't ever get 0 out of this equation for y, because I can't take 1 and divide it by anything and get a 0. So that's why that asymptote is occurring in terms of the function itself. Now we're going to talk a little bit about limits in terms of this picture. And I'll come back to this picture in a moment, draw a little bit more on it. So if we were to consider finding the limit from the right-hand side of 0, of 1 over x, we could say that the limit doesn't exist. So the right-hand side of x means we're over here, right? The right-hand side of 0. And we're on the graph itself, which means we are on this piece of the function, and we're approaching the x value of 0. So we're sort of swooping up. There's an asymptote there. We could say the limit does not exist. Okay, that would be a reasonable thing to say. It's just not very helpful, because there's lots of ways limits cannot exist. So what we're going to talk about in this section is that it's more helpful to actually describe how it doesn't exist. That is, by saying that the limit's infinity. So if it's going up forever, like this one was, right? It's approaching sort of infinitely larger and larger values. It's crossing infinitely larger values of y. We're going to say that the limit is actually infinity. That's a one-sided limit, mind you, right? It's just the limit from the right-hand side that we're referring to here. But we have more information that we're able to convey. We get a better picture of what the graph is doing by saying that the limit's infinity instead of saying doesn't exist, because doesn't exist can happen in multiple, sort of occasions. All right, so thinking about graphs of rational functions, there's a couple of things from algebra that are going to be helpful for us. In particular, finding those particular asymptotes that I just drew in there. So we're going to talk about vertical asymptotes first because they're the easiest ones to do. Vertical asymptotes for rational functions are found by reducing the expression to simplest form and setting the denominator equal to 0 and solving. Okay? And we've done that. You've been doing that with limits. You weren't doing it for the purpose of finding asymptotes, but you were doing it in the last section for the purpose of saying it was discontinuous at certain places, right? And so we've already been doing this. You simplify something and you look at the denominator and find out what you can't have in the denominator. Okay, so setting the denominator equal to 0 and solving, that would give us a vertical asymptote. Horizontal asymptotes are a little trickier. And they're a little trickier because there are 3 possible cases that can happen with a horizontal asymptote. So in the first case, we have the degree of the numerator greater than the degree of the denominator. The second case, the numerator has a lesser degree than the denominator. And in the third case, the degrees are equal. So go ahead and write in all the words that are underlined through here, and then we'll talk about what's really happening, okay? So just jot those in there first, and then I'll talk for a little bit about those. Okay, so if the degree of the numerator is larger, we do not have a horizontal asymptote. So I'll just write an example beside each of these to show you what that looks like. Does anybody remember what degree means? Maybe I should start there, actually. So Some shaking heads of no's. Degree is just the highest exponent. Okay? So whichever the exponent is the largest, that's the degree of your polynomial. So in order for the degree of the numerator to be larger, it needs to be something, or it could be something like this. X squared plus 1 over x minus 2. The degree of the numerator is 2. The degree of the denominator is 1. So there is no horizontal asymptote when this happens. There often is another type of asymptote. We're not getting into that at this exact moment, but there's no horizontal asymptote. Okay? Second case, we could actually just take that equation I just gave you and flip it upside down. Right? The degree of the denominator is bigger. So when we have the degree of the denominator larger, we get the asymptote that actually is the x-axis, y equals 0. Okay, so anytime we have an degree of the denominator larger, we get y equals 0 as an asymptote, horizontal asymptote. And then the last one, the degrees are the same, and this is the most contorted thing to have to write, and it's the simplest thing to do. All right, there's really no simple way to write how to do this, but it's not a difficult process. So let's say that we had 4x minus 3 over 2x plus 1, or something like that. So the degrees are the same, right? They both have degree 1. All this is saying is that you take a ratio means fraction, using the coefficients from the largest degrees terms. So you take the x and you take the value in front of x. So your asymptote in this one would be y equals 4 over 2, and of course we would reduce that to y equals to 2. So you're just taking the coefficients, the numbers in front of the highest degree term, and you're dividing them. Okay? It's not a process that's difficult to do, but it's just so wordy to write down. So we're going to do, we're going to do an example. I thought we were going to do an example next. Okay, so our example is going to start with us finding all horizontal and vertical asymptotes. And then this next part of the directions, the part that often when kids are doing homework or their exams where they don't do this part, I think they just forget because the directions were so long. There's a lot in those directions there. We're going to decide for the vertical asymptotes whether f of x is approaching infinity or negative infinity on each side. So let's start with defining the vertical and horizontal asymptotes, okay? So how do we find the vertical asymptotes? What do we have to do? We have to reduce, and in order to reduce, we have to do something else before that. Factor. So we're going to factor first. Now, the numerator on this one won't factor. It's squared, x squared, and then it's plus 1, so that's not going to happen. If it had a minus 1, we might stand a chance, depending on what the coefficients were of the other pieces, but it's not. So the numerator is not going to factor. We do need to remember that when we're finding vertical asymptotes, that if the numerator does factor, we need to factor it because we need to reduce the fraction. Okay, but this one, only the denominator factors. So how will this denominator factor? Right, x minus 3 and x plus 1. So that gives me negative 3 at the end, and it gives me the negative 2 in the middle, right? Negative 3, oh, sorry. Looking up there funny. Didn't get my x, plus 1. And then it gives me the negative 3 and then the positive 1 to give me a negative 2 in the middle. Perfect. Okay, so using that information, what are my vertical asymptotes?
3 and minus 1.
Right, so we set each of these equal to 0, and we solve them. So x minus 3 equal to 0 would give me x equal 3, and x plus 1 equal to 0 would give me x equals negative 1. I have two vertical asymptotes. Horizontal asymptotes, we need to first identify which case we are in. Are we in case 1, case 2, or case 3? We're in case 3. Very good. So in case 3, we have to, and we're in case 3 because the degrees are of what? The same. And they're actually 2 in this case, right? So we look at the coefficient, that is the number in front of the highest degree term. So what would that be for the x squared that's in the denominator?
1.
It's a 1, yeah. All right, so my horizontal asymptote would actually be 3 over 1, or just y equals 3. Okay. Everybody good so far? All right, this last part is the part that's a little bit awkward. It says for the vertical asymptotes, determine whether the function approaches infinity or negative infinity on either side of the asymptote. So what we're trying to do is you can do it with a graph, that would work. You can do it by plugging in numbers, that would be fine as well. Okay, so take your calculator, it's going to be helpful either way of those you would like to do that. What we want to do is we want to know as x approaches 3, we'll do 3 first since I listed it first, from the right, what is f of x doing? And as x approaches 3 from the left, what is f of x doing? Okay, f of x means y. What kind of y values am I getting? And then we'll do the same thing for -1. X approaches -1 from the left, or from the right, whichever one you do first, and x approaches -1 from the left. Okay, did you guys get a graph that you can see well enough to see what's happening? Let's start with the x equals to, or x is approaching 3. Okay, so you're on the right hand side of your graph, or you're putting in numbers slightly larger than 3. It's going to infinity or negative infinity. It has to. It's an asymptote. Okay, so it's going to do one or the other. So really what you're concerned with is the sign. Agreed? Is the sign negative and getting very, very negative fast, like big, big negative numbers, or are we getting big, big positive numbers? So what's happening as x approaches 3 from the right? Are they positive? In other words, does the graph look something like, here's 3, this on the right-hand side? You have that image? Okay, great. Now what happens on the left-hand side of 3? It's negative infinity. So your image on your graph should look something like this. It's going down if you get close to 3 from the left side. All right, what about -1? That one's over here. -1 from the right-hand side. So it's the kind of, sort of like this area that's sort of trapped between -1 and 3. What's happening from the right-hand side? Is it negative? So the graph must be looking something like this. Yeah? Okay, good. This one's negative infinity. And what about from the left-hand side? It's positive, so it looks something like this over here. Yeah? Great. So these are the pieces of information that they're asking us for in the end. What happens to the function values as the x values get close on either side to those asymptotes? Do they go up or do they go down? Does that make sense to everyone? Now, you could also write this, and I'll write it one more time a little bit differently. And this is fine. This notation is fine as far as I'm concerned. But there is a little bit cleaner way of writing it, and you might prefer that. So let me give myself some space. I'll just cut this for now. Let's say that we were wanting to do this first one. We could say, what is the limit as x approaches 3 from the right of f of x? And we could say it's infinity. And the limit as x approaches 3 from the left of f of x. And that one was negative infinity. So you could also write it with limit notation, because that's what you're really doing. Limits are finding what value you're approaching, and that's what both of these notations actually tell us. So if you prefer that notation, you can use that too. Either one would be fine. Now, I alluded to something a little bit earlier. When I was talking to you about horizontal asymptotes, I made the comment that if the degree of the numerator was bigger than the degree of the denominator, we did not have a horizontal asymptote. And the comment I made was something like, but we might have a different kind of asymptote instead, right? Well, we have a possibility in that case of having a slant asymptote. Now, a slant asymptote occurs when the degree of the numerator is exactly 1 greater than the degree of the denominator. Okay, so just exactly 1, not more than 1. It can't be 3 on top and 1 on bottom, right? It has to be exactly 1. So if it's 3 on top, it'd have to be 2 on bottom for the degrees. Once we do get, in fact, a degree that's 1 greater on top than it is on bottom, we can identify the equation of that slant asymptote by using long division. Long division, you may have thought you'd just never see it again. You will see it again. You'll see it multiple times throughout different math courses, depending on what math courses you take, but it does sort of crop up in unusual places. So let me show you how that works. X squared plus 1 over x minus 2, it definitely falls into that slant asymptote case, right? And we've got a slant asymptote because the degree on top is 1 greater than the degree on bottom. It's the number 2, right? And the degree on bottom is the number 1. So we do have a slant asymptote. We'll do the slant asymptote first, and then we'll go back and do the vertical one in a minute. All right, so the slant asymptote is found by using long division. So what do? Well, I want you to think about what you do when you divide something like 49 divided by 3, because it works the same way. What we do is we do something like, we say, how many times does 3 go into 4? And we would say 1 time, so we write a 1 right here. And we say 1 times 3 is 3, and then we subtract, and we say 4 minus 3 is 1, and then we do the same thing again, right? 3 goes into 19 how many times? 6. 6 times 3 is 18, and then we do subtract, and we get a 1. And then even our answer ends up looking like the same kind of thing. So let me show you, keeping this on here, what happens when we do polynomial division. The denominator still goes on the outside, that's x minus 2. And the numerator goes underneath. Now notice this numerator does not have a term that says x, right? It just has x squared and 1. We need a placeholder. Much like if we had the number 409, as in 0 tens, we'd use 0 as a placeholder. We're going to use that 0 as a placeholder in our expression underneath there, okay? And we're going to look basically at the first terms in each of these expressions, and we're going to say, how many times does x go into x squared? Or an equivalent question would be, what do I need to multiply x by to get x squared? And the answer would be x. So we're going to write an x right there above the x squared, and we're going to multiply. X times x is x squared. X times negative 2 is, very good, negative 2x. Now what did we do once we got the 3 in the other problem? We subtracted. Now the equivalent to subtracting here would be changing all of our signs. I mean, we are going to subtract, but in our problem it's actually going to affect two things, right? We have to change both signs that are subtraction through the subtraction. Now in doing this, of course, the whole point was that these cancel each other out. They add to 0. 0x plus 2x would give me 2x and then plus 1. All right, so next we look at the 2x and the x. What do I need to multiply x by to get 2x? That would be 2. And then we'll multiply. 2 times x was the 2x we said. 2 times negative 2 is negative 4, right? And then what do? We change our signs. We subtract. So the 2x and the negative 2x, those cancel out. And I'm left with 5. Okay. Now we could write down that the original function that we were given, I mean, like this function that we were originally given, in fact, I'll write it just so you can see it. It's actually equals x plus 2 plus 5 over x minus 2. That would be the mixed number version of this form. Okay, and that's fine. I mean, we can write that. It's not especially helpful. It doesn't answer the question that we're being asked. We're being asked what the slant asymptote is. Well, the slant asymptote is the part that divided out. It's right here. And it is an equation, so we're going to write y equals. So our slant asymptote on this one is y equals x plus 2. That gives us a diagonal kind of a line. And on the ends of that line, we actually get close to that line instead of a vertical line or a horizontal line. So let me do the vertical line with you, and then I want you to graph it so that you can see this graph does, in fact, look a little bit funny. What is the vertical asymptote for this graph? 2, but we want to say x equals 2. We're dealing with lines, and we want to make sure that we're saying x equals or y equals because they do form different lines. So our vertical asymptote is x equals to 2. Our slant asymptote is y equal to x plus 2. Do you guys see a graph for that? It sort of feels like it's tilted, right? And you can't see it necessarily drawn in there because your calculator won't draw it in, but if you put this equation, the original equation, in y1, this one right here. And if you put your slant asymptote into y2, you will see that on the ends they almost match. They get very, very close to one another on the ends. So you can confirm this answer very quickly graphically in your calculator by plugging both the slant asymptote and the original function in and verifying that they do in fact sort of almost merge as you get towards the edges of the graph, of your screen. Is everything looking okay? Yes?
Can you use synthetic division?
You have to be careful because synthetic division only works if you're dividing by something that's linear. So yes, you could use synthetic division on this one because x minus 2 is linear. The problem is that if you don't have something linear, it doesn't work at all. And then you're sort of left. So I usually avoid talking about synthetic division because it only works in a very, very limited, domain. And that's kind of the problem with it. So if you were to use synthetic division on this problem, I'm not going to count anything off for it. That's okay. Just recognize that it's not going to always work. So yeah, that's a good question. Okay, did we get the calculator to work out okay here? It's all good? Okay, did everybody see a screen like I was describing? We're all good with that? Excellent. All right, theorem 5.1 kind of goes a little bit further out from here. It says for any rational number t greater than 0, if we have the limit as x approaches plus or minus infinity of 1 over x to the t, it equals 0. For the case where x is approaching negative infinity, we have to assume that t equals p over q, where q is odd. Trying to think what I want to say to explain that a little bit. You'll write that down and then I'll think. If we were dealing with a value t where q was even, the way that they've described this, that is if we could write it as a fraction and q were even, we'd actually end up with like a square root or a fourth root. The problem with that, and we've seen this happen before, is that when we end up with an even root, we only have half of a graph, quote unquote, right? Because we can only enter positive values underneath a radical. We've talked about that a number of times. So this information here at the bottom is just telling you that when you're dealing with this theorem, that it's trying to assume that you're having a domain where you've got positive numbers and negative numbers. The only way you're going to have positive numbers and negative numbers is if you have any radicals. You're talking about radicals that are radicals that would be odd powered radicals. So that's what that's getting at. The crux of the problem is actually telling you that the limit is always 0 when you have a t value that's greater than 0 here. Okay, we'll see it play out in a little bit here, I promise. Polynomials are a little more interesting. So when we have a polynomial, and people don't like this notation for some reason, but you often are familiar with sort of a trinomial. It's ax squared plus bx plus c. A and b and c are just numbers, right? Well, in this case, this a sub n, this a sub n minus 1, all these are just numbers as well. It just allows us to have as many of them as we need. If we only are using letters of the alphabet, then in theory we can only have 26 of them, and really not even 26 because we couldn't have x or y because we're already using them for something else, so that wouldn't work very well. So we're just talking about a polynomial, okay, something that's like quadratic or cubic, powers of 4, things like that. If you have the limit of a polynomial, it's going to be infinity if a sub n is greater than 0, and negative infinity if a sub n is less than 0. And I think a picture helps to discuss this very well. So, and this is the limit as x approaches infinity. So take a look at a graph. Maybe I should go back and draw a graph on the previous one too. That might be helpful. All right, so this is saying that x values as you approach infinity. There are really 2 possible graphs I'm going to draw. I'm going to draw 2 of them. I'll draw this first one. What is that a shape of? It's a parabola, right? This is a parabola. This is a parabola opening upward, so this is assuming that the first value here is a positive number. Now, no matter whether we have a power of 2, which is a parabola, or a power of 4, or a power of 6, or a power of 8, whatever, no matter what we have, the ends of the graph, if we have a power that's even, look like this. They point up. okay? And if we have a graph where, I'll draw the graph of the cube next. Let's do that. If you have a graph of x cubed, you have one of the ends pointing down like this. And again, no matter what power you're dealing with, whether it's 3 or 5 or 7 or 9, odd powers, you always have one pointing down. Now, this graph right here is only talking about x values going to infinity, so we're only looking at pictures of the graph that are on this side of the graph. We're only talking about x values going to infinity. So my point being is that this is x going to positive infinity. So if this is my x-axis and I'm going to positive infinity, then I'm moving along the x-axis in this direction. We're not approaching a number. We're getting infinitely larger values of x. Okay? So as x approaches infinity, in this graph, we're going like this. Okay? And we were doing that in the parabola kind of graph too, right? I didn't erase that portion of the graph. It's the same. Whether it's a parabola shape or a cubic shape. Both of them are the same. It has that sort of sweeping upward pattern on the right-hand side. Okay? Now, that's telling you then that this graph is going up forever. That means positive infinity. But that's happening because this a sub n value is positive. What happens on a parabola if you have a negative in front of the x squared? Like what happens on this graph compared to this graph? Reflected over the x-axis, that was said very well, yeah. It flips down, right, or it opens downward. It's reflected across the x-axis. So my picture ends up looking like this. It plummets instead of it raising, right? So if the leading coefficient, like this a sub n value, is negative, it's going to go down on the right-hand side indefinitely, like forever, all right? That's why this one's approaching negative infinity. So this is saying a sub n is negative. It approaches negative infinity. If a sub n is positive, it approaches positive infinity. Okay, it's all based on the first term, the leading coefficient, the term of highest degrees coefficient. All right. So what we're going to do is we're going to, I said I was going to go back and take a picture or show a picture of you for you with what this looks like. We drew a picture before, but let me just draw it again. All this is saying is that we have a graph of, again, it's going to positive and negative infinity. This is the graph I drew just a minute ago, roughly, right? Okay. So this is saying at the very ends of this graph, what y value are we approaching? 0. It's getting really close to the x-axis, right? So that's visually what it's describing. That's the picture you're getting from that. All right, let's do some examples. It says to determine each limit, answer as appropriate with a number infinity, negative infinity, or does not exist. So when we're dealing with this one is just a rational function, all right? Just a plain old rational function. And if it's a rational function, then the limit corresponds to the horizontal asymptote. So if we can talk about what is the horizontal asymptote, then we know the limit. That's the same picture I just drew over here. The horizontal asymptote here was the x-axis, right? It's y equals 0. So that's the limit at the ends, 0. So if we've got a rational function, all we need to do is to find the horizontal asymptotes. So what are my horizontal asymptotes here? Or what is my horizontal asymptote here? 1/2. Where'd you get 1/2, Matt? You're right.
The degrees on both top and bottom are the same, so it's just the numbers in front of the x squared.
Good. So the degrees are on top and bottom are the same, so it's case 3. So I take a ratio of the coefficients, so I get y equals 2 over 4, or we can simplify, of course, to y equals 1/2. So that 1/2 is creating this horizontal line that on the edges of the graph we're getting very, very close to. So the limit then, as we approach infinity, of our function, we'll call it f of x, is going to be 1/2. Because that's the horizontal asymptote it gets close to on the end of the graph. Now, number 4 is not quite a rational function, right? What is it about this one that makes it not a rational function? That square root, man. That square root does not make it a rational function. However, this is similar to the case we had back on Theorem 5.1. So if you flip back over to Theorem 5.1, it's not 5.1, but it's similar to Theorem 5.1. 5.1 says that if we have something where we've got a rational denominator, it has a radical form of sorts, which we do have a radical form here, the limit should be 0. So the difference is that this one has a numerator. It doesn't just have a 1 on top. Agreed? Now you guys have dealt with these a little bit when you were working in the last section. You haven't dealt with them from this perspective, but you did deal with sort of trying to simplify or see if you can look at radicals and denominators and what they do, factoring and sorts of things like that. So think with me for a moment. Right now, what is the degree of the numerator? It's 1. The degree of the numerator is 1. What is the degree, or the sort of degree, if you will, of the denominator? It's actually 1 as well. So why do you think it would be 1? Some of you are saying 2, and I know why you're saying 2. So where would 1 come from? Yeah, we've got a square root and we've got an x squared. Now we can't really take the square root of the x squared by itself, right? I mean, like, we recognize that, but there is that operation there that is affecting it somehow. I mean, we're squaring something and we're taking a square root, so we're sort of undoing parts of this somehow by themselves. So in terms of sort of finding out, this actually does have, I'm going to cut that out first, it does have a horizontal asymptote. The horizontal asymptote is actually going to occur very much like what we did in the last one. We can take a ratio of the coefficients, but it's a little trickier. So let me show you what I mean by that. So the number 4 underneath there doesn't really affect much of the graph. All right? It just has very little effect on what's going on. So we can rather ignore it for what we're doing, and we can reduce this, but here's the catch. What's the square root of x squared? It's actually plus or minus x. Very good. The reason I say plus or minus x is because if x is positive, then one thing happens, right, on the graph, and that would be the right-hand side of the graph. And if x is negative, something else happens on the left-hand side. This one's the limit as you're going to the right-hand side. So for what we're working with, our x values are going to infinity. These are positive values. So we're dealing with basically having negative x over a x. Our x value in the denominator is a positive value. So this gives us a, what number? It's -1, indeed. So my horizontal asymptote is -1, so my limit as x approaches infinity of the function value is also -1. And again, you can confirm that by a graph, right? Graph it. See, does it level off at x equals 1? I'm sorry, at y equals 1. Use your table. Put in infinitely large values. We haven't done that yet, but if you're set up your table like we did before, you can pick what x values you put in. Well, pick some big x values. Try x equals 10, and then x equals 50, and then x equals 122. I don't know. Try big x values and see what happens. If we're right, they should be giving you values very, very close to -1. So you can confirm your suspicions. You can verify your work by using your calculator as a back of the book kind of thing, basically, right? So even if it's an odd, an even problem where you don't have the answer in the back, you can confirm that your answer is correct. Okay. Does everybody see that okay on their calculators? Those of you who are looking, everybody all right? Okay, we're going to try one more example. Same directions, of course. This one wants us to find the limit, and what's different about this one? There's a sign in it, right? Now, if the sign weren't in it, just pretend you sort of block it out. You know, put your hand on top of sign and pretend like it's not there. If it weren't there, this would be a rational function, right? No problem. We'd have x squared on top, x squared on bottom. This would be a case number 3. It'd be straightforward, simple, right? Agreed. Okay, but the sign does sort of some strange things. Now, I've had a couple of you in my office, and we've talked a little bit about sign from a different perspective. But what values come out of sine? I don't care about what goes in. I know you can put any input you want. But what output values do you get from a sine function? Was it? From -1 to 1, right? It's trapped. If you remember the graph of sine, it oscillates up and down a wave pattern, and it's trapped between -1 and 1. We use the phrase bounded. So sine x is bounded. You can also write for yourself that -1 is less than or equal to sine of x is less than or equal to 1. So in a very real sense, all we really have on the numerator next to the 2x squared is we have a value between -1 or 1. That's all we have, right? It's just like multiplying or dividing by a value right beside it. That's what we've got going on. So our limit as x approaches infinity is basically oscillating via plus or minus. I mean, it's going to be going back and forth between a positive and negative. And then we have 2x squared, and we can consider just the x squared, much like when we were looking at the case 3 examples, right? It's oscillating, it's plus or minus. But the x squareds are our highest degree, and those would reduce. So we end up getting what on this for a value? Plus or minus 2. So just like sine bounced up and down between positive and -1, this graph bounces up and down between positive and -2. So if we go to the right forever, plugging in infinitely larger and larger and larger values, and it keeps bouncing up and down between positive and -2, what's the limit? Somebody guess. What do you think? What's going to happen? What if I asked you the question? Let's just take sine x itself for a second here and talk about it. You know, you have a picture in your mind without even graphing it of sine x, because we've all had trig at some point in the fairly recent history, I'd say, most of you. So you have a graph in your mind of sine of x. And if I ask you the question, as you go to the right-hand side forever of the graph, what y value does sine of x approach? What would you say? Plus or minus 1. Okay, but what y value does it approach? You just gave me 2 of them. I mean, it can't approach +1 and -1. Does it approach 0? Every bit as much as it approaches positive or -1. It keeps crossing the x-axis, right?
All real numbers.
No? It doesn't exist, guys. It doesn't approach one value. It keeps bouncing up and down, doesn't it? Well, the same's true for this graph. This one's just bouncing up and down between positive and -2. So we've got a graph doing this. A limit has to be a value you get close to. There is no value this gets close to. Right? It keeps bouncing. So this limit does not exist. You can't approach positive and -2. That doesn't work. Now, let me just say, what happens in this equation? I don't think you're going to encounter that, so I'm going to pause. We'll take a step back there. I won't approach it. But I will say that what I said before, I'll write it down. This oscillates. Between +2 and -2. So there is no limit. It doesn't approach any particular one y value, which is what a limit actually is. It's a particular y value you're approaching. Any questions on that one? Now, let me just take a couple minutes to show you what we just did. We don't have quite time enough to do group work anyway, so let me just make a couple more kind of concluding comments on this. This whole section's point is saying that saying a limit doesn't exist is not very helpful if you could say it's positive or negative infinity, right? So on these ones here at the end, whoops, where I actually have limit values existing at 1/2 or at -1, but I had some examples here as well where we were talking about polynomials being infinity or negative infinity. It gives me an image of what's going on the graph. If I just said doesn't exist all of those times, you wouldn't know. Now this last one, I'm left sort of in a quandary. I don't have anything else to say. It doesn't approach a particular value. So the only thing I'm left with then is by saying does not exist. So what we're doing in this section is we're trying to give more detail about the limit. Even if we're saying that a limit is supposed to be a number, and of course infinity is not a number, it does give us a better concept of what's really going on with our function. Does that make sense? Okay.